ASDIP Foundation includes the design of strap footings, which is a system consisting of two spread footings tied together by a strap beam. But how do you actually design a strap footing system when one of the footings is eccentric, as in this case, or when you have out-of-plane moments? This is Javier Encinas, and today we're going to design completely from scratch a real-life example of a strap footing system. Let's get started. In this example, the columns are spaced 20 feet apart, and the property line is very close to the exterior column. So an eccentric footing would be necessary. In these cases, the exterior eccentric column would cause an isolated footing to tilt. This can be prevented with the use of a combined footing. However, since the column spacing is 20 feet, the cost of large excavation would be excessive. The solution is a strap footing, as shown here. The strap beam produces a rigid system that resists the resulting in-place shears and moments, preventing the tilting of the exterior footing. The loads are dead load, 4 kips and 80 kips in the exterior and interior columns. Live load is 40 kips and 60 kips. The wind load is 40 kip feet and 50 kip feet out-of-plane moments. So moments around the x-axis. So let's go to ASDIP Foundation to model this system. When you open ASDIP Foundation, you see the project manager. Here you can see the modules included in the package: spread footings, strap footings, combined footings, wall footings, pile caps, and pile analysis and design. In this case, we're going to create a calculation for a strap footing. I have already created an example. So let's double click on this node in the tree. And this is the template for a strap footing design in ASDIP Foundation. Let's go to the Loads tab to enter the information given in the statement of the problem. Here I have entered information already. Dead, 40 and 80 kips. Live is 40 and 60 kips. And wind, out-of-plane moments, 40 kip feet and 50 kip feet. So all the loads are already entered here. Let's go to the Geometry tab. Here you can enter all the information related to the dimensions of the footings and the strap. Let's click on the Graph tab at the right to see what we are doing. I have entered some information as a preliminary design. The exterior footing is 4.5 feet by 7.33 feet. It's shown graphically here. The interior footing is 6.67 feet square. All these dimensions are preliminary and can be changed later on to optimize the design. Since this column is very close to the property line, this footing, the exterior footing, needs to be eccentric. So it's advisable to be narrow in this dimension and large in the perpendicular dimension. That's why I have selected these preliminary dimensions. As you can see, the program immediately calculates the bearing pressures at the footings. In this case, the maximum pressure is 3.2 kSF and the minimum is 2.3. For the concentric footing, the maximum pressure is 3.4 and the minimum is 2.5. If we go to the Materials tab, here we can see in the Soil tab that the allowable gross bearing pressure is 3.6. So with these dimensions, the bearing pressures are under the allowable limit. Go back to the Geometry tab. So now we have verified that the pressures are okay with these dimensions. So let's focus now on the thicknesses and the reinforcement. Let's go to the At a Glance tab. This is a summary of the results just in one screen. Here you can see immediately if something is failing. In this case, everything is passing, so we need to optimize the design now. Let's focus on the exterior footing now. The thickness of the exterior footing is controlled by shear. This footing now is 24 inches thick. We can see here that the one-way shear ratio is 0.44 and the punching shear ratio is 0.27. So there's a room for improvement here. So we can reduce the thickness to make it more efficient. Let's say 18 inches. Now the ratio is 0.71. It's probably okay. We can reduce it even more if we want. Let's see, 16. 0.84, okay? So let's leave it the way it is. Now in the interior footing, the ratio is 0.52 and the thickness is 18. So let's change it to 16 inches as the exterior footing. and the ratio is 0.64. So the thicknesses are okay now with 16 inches thick. Let's go back to the graph tab, the diagrams. The program generates the shear diagram and the moment diagram for the strap beam. With this information, the program is able to calculate all the rebars that are necessary in this design. The minimum and the maximum shear along the beam, and the minimum and maximum bending moment along the beam. Let's go to the reinforcement tab. Here we can enter all the information regarding the rebars for the footings and for the strap beam. Let's go again to at a glance and focus on the strap beam design. Here we can see the ratios for shear and for flexure. The maximum ratio is 0.51. So there's a room for improvement here. In the geometry tab, if we click on the strap beam tab, we can see the dimension that we selected for this beam, 18 by 24. We can reduce that if we want. It's probably better if we keep these dimensions, which are pretty much typical, and just reduce the reinforcement accordingly to optimize the design. So let's go to the reinforcement tab, strap beam design. The beam has 5 bars, number 8 at the top, and 5 bars, number 7 at the bottom. For the top bars, the ratio is 0.51. So we can reduce this, let's say number 7 to be consistent with the bottom. Now the ratio is 0.65. We can reduce the number of rebars, maybe 4 instead of 5. And the ratio is 0.81. So we can leave it as it is. To be consistent, let's use the same reinforcement at the bottom for number 7 as well. Regarding the stirrups, we are using number 3 at 9. With this reinforcement, the maximum spacing ratio is 0.89. And the one-way shear ratio is 0.19. So it's very comfortable as it is right now. So let's leave it with that reinforcement. Let's focus now on the reinforcement for the footings. Here we can see that in flexure design, the maximum ratio is 0.52 for the X bars and 0.29 for the Z bars. So let's optimize that reinforcement. Remember that the footing is only 4.5 feet wide. Let's use 5 rebars instead of 12 in that direction, and let's see the effect. Now the ratio for the Z bars is 0.66. Let's see if we can use rebars number 5 instead of 6, and the ratio is 0.92. Minimum steel area is failing, is very close to the limit. Probably we can use 6 number 5s. And now we are okay. So the ratio is 0.77 and the minimum steel area ratio is 0.84. In the other direction, the dimension is 7.33. So let's try to increase this ratio, reducing the number of rebars. Let's say 10 rebars, number 5, to be consistent. And the ratio is 0.87. So everything is passing. Now let's focus on the interior footing now. This footing is concentric and is square, 6.67 feet. And the bending ratios for X and Z rebars are 0.45 and 0.47. So we can reduce the number of rebars to 10. And now the ratio is 0.63. The minimum steel area ratio is 0.83. So it's very well optimized as well. Everything is passing in this design, but let's see this ratio, which is 0.99, is very close to the limit for one-way shear in the exterior footing. So probably we need to increase the thickness of that footing a little bit. Instead of 16, let's say 18 inches to be more comfortable. Now the ratio is 0.84. Let's go to the condensed tab. Some more detailed set of calculations, the exterior footing design. For the interior footing, which is concentric, in the design of the strap beam, the program also checks the transfer of the load from columns to footing. Let's go to the detail tab. This is a more detailed set of calculations, step by step, with exposed formulas and also with references to the ACI code. And finally, in the construction tab, here the program generates some sketches in elevation and in plan view, showing all the rebars in the final design. As you can see, it's very easy to design strap footing systems in ASDIP Foundation. we were able to finish and optimize the design in just a few minutes. If you like the software, please visit the website www.asdipsoft.com and download the free 15-day trial. Please subscribe to the channel if you want to receive notifications in the future for similar videos. Thank you for your attention.